Alright, so let's try to size up the error. Start off with a generic statement here. You got a function, you got the nth degree polynomial approximation, and you've got what's left over. What this guy says, amazingly brilliant, says, hey, I've got a way to take that entire remainder, even though it's really long, infinitely long. I mean, it is really long. Like, there's more terms here than there are atoms in the universe. That's how long it is. Lagrange says, I've got a way to compile all that and get it into a nice little form. It will be like this. The remainder will be the nth remainder will be the n+1th derivative at some point z. I'll tell you more about that. You may not even know what that point z is, and it may be really difficult to find. But I'll tell you more about that later. Lagrange says it's the n+1th derivative at some point c times the term here that look like the terms on there. X minus c, where c is the point where the Taylor expansion is being expanded about, and you got n+1 on the bottom. Right, c will be some number that we may not know that's between c and x. Okay, that's where z comes from. You can make a little note here. If you like, z comes, you could make a little thinking bubble here, just so we don't forget. Z comes from x and c, somewhere within x and c. Alright, so how do you prove that? Well, you have to pay extra to see the proof, but it's an amazingly brilliant proof by Lagrange. There's actually another one by Cauchy, blah blah blah. I may put that in another video if people pay extra money. But the important thing is, how do we use this? Let me show you how elegant this is. This is a way of controlling exactly how bad your error is after some given approximation is decided upon. Take this for example. Suppose you have sine, and you wanted to see, hey, if I just measure how different is sine from the fourth approximation, this would be the error expanded about x equals 0, and it's in this interval. I'll give you a picture of what that looks like. That looks roughly like this. It looks like you have your sine function. The sine function looks like this, and it goes like that forever. And you have the degree 4 polynomial approximation. This would be the degree 0, this would be the degree 1, degree 2, degree 3, degree 4. So roughly speaking, maybe it looks like this. This would be the degree 4, this is the degree 4 approximation, and this would be the sine. And near here, they may be really close to each other, but as the further away you get, the worse the approximation gets. Here, obviously, the error gets really big. So what if we confined our analysis to just this period between -π/2 and π/2? So between π/2 and -π/2, we're asking, how bad could things get if we replace our sine of x with our degree 4 polynomial? Degree 4 polynomial will look like this: x minus x to the 3 over 3 factorial plus 0 x to the 4 over 4 factorial. That's what the expansion is, because we've done it many times. In fact, a lot of people don't even write that sometimes. You don't have to write it if you don't want to, but that's the degree 4 polynomial approximation of sine x. And it's not really true to say e equal. What's more true would be to say that it's equal to that plus the remainder, r4. Yeah, that would be equal. But if you take this away, then it's not exactly equal. And we're trying to figure out how bad is this thing get. That's what we're doing. Now here's how you do it. You say, you know what, R4, we have an amazing formula that was invented by Mr. Lagrange here, Dr. Lagrange, who wrote letters to Euler, right? And Euler tried to make him feel good, withholding the discoveries that Euler had already done. Okay, I digressed. Lagrange invents something and says, you know what, R4 of x is equal to, for this I have to look at my excellent formula. R4 would be equal to f4 plus 1 at some point z between x and c times all that. That's what we got to do. Wait, I think I had it right here. So, so the fourth ordered remainder would be the fifth derivative of the function at some point z, and you plug in n equals 4, so I plugged in 4 there, 4 there. That reduces to something like this. And now I want to know, well, how bad can that get? Well, let's figure out the fifth derivative. I know that the function was sine of x, so that the first derivative would be equal to cosine of x. I know that the second derivative would be the derivative of the cosine, which would be negative sine of x. I know that the third derivative would be the derivative of that, which would be equal to negative cosine of x. I know that the fourth derivative would be equal to the derivative of that, which would be sine of x. And I know that the fifth derivative would be the derivative of that, which would be cosine of x. So the fifth derivative, this guy, is equal to cosine. The fifth derivative at z would be cosine z. And I know that z, cosine z, can never be bigger than 1 because this ratio of adjacent over hypotenuse on a real angle, that the adjacent would always be smaller than or equal to the hypotenuse. So this is no bigger than 1. I left this alone. That gives you this inequality. Okay, and then the 1 times anything would be that same thing. That gives you this inequality. And we know that our x's, the assumption was that our x's are coming from this range. In fact, both your x's and your z's are coming from this range. Because z is always stuck between 0 and x is always in here. That forces z to always be in there. And in that range, well, in fact, in any range, cosine z is less than 1, but that might be useful in other problems. Your z's and your x's come from this range. Okay, so my x's are no worse than pi over 2 in absolute value. That gets me an actual bound for the error. And I can put this on the calculator and I can gather that the fourth order remainder is no bigger than about 8%, 0.08. It's nice, huh? It's Lagrange, man. Put all the errors, all the remainders, all the tail into one item, and easily. Once you get to this point, once you put it into the formula here, you figure out the formula for the fifth derivative, you figure out where your z's and x's come from. Your z's and x's come from whatever interval you're looking at. It's impossible to look at it, well, it's not, sometimes it might be hard to look at it over the whole interval because your polynomials are only good near the point unless you take longer and longer expansions. Okay, so that leaves us with the conclusion of the question: how bad is the error if we use the fourth degree polynomial approximation and we stick the x's within this boundary, and we concluded that the error can be no worse than 0.079 blah blah blah. That's it. That shows you how to find the error. Okay, come back, we'll do another example.